System Design Fundamentals, a complete guide. When building large-scale distributed systems, understanding these fundamental components is crucial for creating robust, scalable, and efficient architectures. Let's explore each element and how they work together to solve real-world challenges. Scalability, the foundation of growth. Scalability represents the system's ability to handle increasing loads gracefully. The diagram shows this as an expanding box with an upward arrow, symbolizing growth. There are two primary approaches. Vertical scaling, scale up, adding more power to existing machines, more CPU, RAM, or storage, while simpler to implement, it has physical and cost limitations. Horizontal scaling, scale out, adding more machines to distribute the load. This approach, represented by the expanding boundary, offers virtually unlimited growth potential and is the cornerstone of modern distributed systems. Load balancers, traffic distribution masters. Load balancers act as intelligent traffic directors, distributing incoming requests across multiple servers. The diagram shows this hierarchical distribution pattern where requests flow through load balancers to reach backend services. Key benefits include high availability. If one server fails, traffic redirects to healthy instances. Performance optimization distributes load evenly to prevent bottlenecks. Flexibility enables seamless scaling and maintenance operations. Popular algorithms include round-robin, least connections, and weighted distribution based on server capacity. Object storage, scalable data repository. Object storage systems provide virtually unlimited storage for unstructured data like images, videos, documents, and backups. The cylinder with various geometric shapes represents the diverse data types stored as objects. Modern object storage offers durability, data replication across multiple locations, accessibility, RESTful APIs for easy integration, cost-effectiveness, pay-as-you-use pricing models, global distribution, content delivery through edge locations. Message queues, asynchronous communication. Message queues enable asynchronous communication between system components represented by the cylindrical queue structure. They decouple producers from consumers, allowing systems to operate independently. Benefits include reliability, messages persist until successfully processed, scalability, producers and consumers can scale independently, resiliency, system continues operating even if components are temporarily unavailable. Load leveling smooths out traffic spikes by buffering requests. Microservices, modular architecture. The connected hexagonal nodes represent microservices architecture, where applications are broken down into small, independent services. Each service handles a specific business function and communicates through well-defined APIs. Advantages include independent deployment. Services can be updated without affecting others. Technology diversity. Different services can use different programming languages and databases. Fault isolation. Failures in one service don't cascade to others. Team autonomy. Small teams can own and maintain individual services. Caching. Performance acceleration. Caching stores frequently accessed data in fast storage layers, dramatically reducing response times. The diagram shows this as a database with a lightning bolt, symbolizing speed. Common caching strategies include in-memory caching, Redis and Memcache for ultra-fast access, CDN caching, geographic distribution of static content, database query caching, storing expensive query results, application-level caching, custom caching logic within applications. Database, persistent data foundation. Databases provide reliable, persistent storage for structured data. The traditional cylindrical representation shows the foundational role databases play in system architecture. Modern considerations include ACID properties, ensuring data consistency and reliability. Replication, master-slave or master-master configurations for availability, sharding, horizontal partitioning for massive datasets, NoSQL options, document, key value, and graph databases for specific use cases. CAP theorem, the fundamental trade-off. The CAP theorem states that distributed systems can only guarantee two of three properties simultaneously: consistency, availability, and partition tolerance. The overlapping circles illustrate this fundamental constraint that shapes all distributed system design decisions. Most modern systems choose between CP, which is consistent and partition tolerant, or AP, which is available and partition tolerant, based on business requirements. Rate limiting, traffic control. Rate limiting protects systems from abuse and ensures fair resource usage. The funnel diagram shows how traffic is controlled and throttled to prevent system overload. Implementation strategies include token bucket, allows burst traffic up to a limit, fixed window, strict limits per time period, sliding window, more flexible time-based limiting, distributed rate limiting, coordinated limiting across multiple servers, partitioning, data distribution strategy. Partitioning divides large data sets across multiple storage units to improve performance and manageability. The diagram shows data split into logical partitions. Common partitioning strategies include horizontal partitioning, or sharding, splitting rows across multiple databases, vertical partitioning, splitting columns into separate tables, functional partitioning, separating data by feature or service, hash-based partitioning, using hash functions for even distribution. CDN, Global Content Delivery. Content delivery networks distribute content globally through edge servers, reducing latency for users worldwide. The globe with surrounding nodes represents this geographic distribution. CDN benefits include reduced latency, content served from nearby edge locations, bandwidth optimization, offloads traffic from origin servers, improved availability, multiple points of presence provide redundancy, enhanced security, DDoS protection, and traffic filtering. Stream processing, real-time data flow. Stream processing handles continuous data flows in real time, enabling immediate insights and actions. Use cases include real-time analytics, instant metrics and dashboards, event processing, immediate response to business events, data transformation, on-the-fly data enrichment and filtering, alerting systems, immediate notifications based on data patterns. Integration and synergy. These components work together to create robust distributed systems. A typical architecture might use load balancers to distribute traffic to microservices, which communicate through message queues, store data in partitioned databases, cache frequently accessed information through CDNs, and serve static content through CDNs, while processing real-time data streams while respecting rate limits and the CAP theorem. The key to successful system design lies in understanding how these components interact and choosing the right combination based on specific requirements for consistency, availability, performance, and scalability.